So my name's Jake Wharton. I'm here to talk to you about using Kotlin multi-platform with languages other than Kotlin. So not all libraries are written in Kotlin. This is like an easy truism, right? There are people in this room right now talking about libraries written in other languages. And then there's, not millions, thousands of other languages with millions of libraries. And it's every week you're going to see somebody in, Kotlin Lang Slack asking for some library that doesn't exist. Like, hey, I want to show a map and compose multi-platform, or I want to do this hyper-specific thing that I can do in this other language, but there's nothing turnkey for me in Kotlin, and that's okay. But I'll even say that while those libraries will eventually get built, not all libraries should be written in Kotlin. There's just things about Kotlin's execution mechanisms that don't lend themselves well to every single library. You wouldn't think that like the Java virtual machine should be written in Kotlin, or how about like the file system running your computer, or something like Git is probably not appropriate to be written in Kotlin, and that's okay. And I'll take this even further and say that really the best libraries in the world, irrespective of language, are not going to be ones that are written in Kotlin. If you try and think like, what's the best library, open source library in any ecosystem? For me, things come to mind like curl or FFmpeg was one we talked about yesterday. It's like these things that are just the toolkit that you turn to, and they're not written in Kotlin. Not necessarily because Kotlin's the wrong fit for it, but it's more that these other languages serve the use cases better by having lower level access control to memory or operating system APIs, or even the ability to do things sort of natively that are unavailable to virtual machines. But just because these libraries are written in other languages does not mean that we cannot still leverage them from Kotlin. So almost every library that you can think of that comes from some other ecosystem is probably still able to be leveraged in Kotlin, despite the fact that it's written in another language. And we don't want to take that other language away from them. We simply want to utilize the advantages that they provide while still, for us, staying in our comfort zone, which is the Kotlin programming language. And I want to take a look at a couple of these examples. And I'm going to start with talking about just Kotlin multi-platform in general and how we think about it. So if you have a problem where a library doesn't exist that you need to solve, like logging, say, you might go and say, ask in Kotlin Slack, how do I do this? How do I log on multiple platforms? And if somebody doesn't give you a library, they probably are going to say, well, if you need to target all these different platforms, there's a mechanism in Kotlin for that, and that is the expect actual mechanism. So you define your expect for the logger, and then you go to each platform that you want to support, and you write the actual implementation. And you do this once for every single platform, or at least once for every set of targets where the APIs are common. And so this shape of making something multi-platform is very, it's like a tree. It's like fan out. We're fanning out to platform-specific implementations of this common necessity that we're trying to write. And that's fine. This works very well for simple things, but let's say you want to go from logging to like rendering an entire UI. Well, this strategy is not going to work. You're not going to want to take the entirety of a UI toolkit, which is rendering, has this whole graphics and text stack, and rewrite it on every single platform. That's just going to become a maintenance nightmare. So instead, what we do is we find something that's common further down the line, and we fan back in to leverage that existing common thing so that all that's left for the platform-specific bits are these pieces of glue code that really get us back to this shared thing. So Skia is this library on which Compose UI, or I should say it's the library on which Android's rendering is built. And when Compose UI went multi-platform, they were able to take the existing Skia code and port it to other platforms so that they didn't have to rewrite this entire UI toolkit. And so this is more of like a diamond shape, where before we're just fanning out to platform-specific representations. Now we're doing this diamond where we fan back in to have this high leverage, high value shared code that happens to be written in another language, but that we can now reuse. So Skia is this library from Google, and it's a C++, primarily a C++ library. And so what JetBrains has done is they've wrapped this in a Kotlin multiplatform API. Primarily, it targets the platforms and it's basically for Compose UI. Technically general purpose, but focused on the Compose UI usages. I gave a talk at KotlinConf last year about this ridiculous project I did, where I got Compose UI running on a light switch, and it actually is built on top of Skia and Skiko. And so this is a Kotlin native project, and somewhere down here, I call into Skia and Skiko to get this thing called, what am I looking for here? Right here. I call this API. This is a Kotlin multi-platform API that returns me a surface on which I can draw things. And that surface gives me a canvas. And if you're an Android developer, you might recognize Canvas's API because you can do things like, draw rectangles, draw circles, there's text. The Skia Canvas API was basically copy-pasted in Android 1.0 to be Android's Canvas API. But this is not an Android project. This is a Kotlin native Linux ARM project, and I'm still able to leverage that same API through the fact that JetBrains has taken this and wrapped it in Kotlin multi-platform. And so what I want to do is I'm going to show this project and a couple other projects. We're going to take a look at how they work, how they're basically going through and doing this commonization of libraries that are otherwise written in different languages. So I'm now in Skiko, which is the wrapper. And this is the common abstraction. So we start off very different than like the logger example. We're not in an expect class. And this is that API that I was calling. You can see it basically just forwards to this function. And here we see things that you probably don't see regularly in Compose code. We have an external function, which is telling the compiler that some other system is going to fulfill the implementation of this. And then there's these references to sort of these weird names, which are unexplained, but you can kind of get a hint here, maybe that this one's probably for JavaScript. And then if you actually click into these, you can find that they're for native or JVM. And so what's happening here is that there are native versions. So this is now C++ code. There are native functions written in C++ that have this ridiculous name, this long name, that are becoming implicitly bound to that Kotlin reference. And what this function is doing in Skiko is just delegating to a Skia API. So they're basically taking an API that is Kotlin appropriate. So you can see we're getting like Kotlin native pointer inputs and Kotlin integers, and they're adapting it to work with Skia's C++ API. And then from the Kotlin itself, they are, my numbers are all off by one. They are binding to that through this annotation and this method call. So when I call the common code on native, it's going to then call into their Skiko C++ code, which then calls into Skia's C++ code. And the same thing works on JavaScript with both running in JavaScript, but loaded WebAssembly, or if you're just running in WebAssembly directly. And then the last thing is just the JVM. So this is also C++ code, but it's the JVM version of the C++ code. So the parameters to this function now are different. They're Java things. We're getting the Java environment, the JNI environment, the Java class that the method is in. You'll see it has a similar but slightly different name. It's got like this Java prefix There's a real subtle one here where this one has surface KT, and the other one was actually just surface. I'll talk about that in a second. But then they're doing the exact same thing over again, where they're just turning these Java values into native Skia values and then delegating to that shared C++ code. So all they're doing is writing platform-specific glue code in C++ because Skia is a C++ library, and then writing a single common Kotlin representation of that API and like linking against it. All right. The one thing I want to mention is for the Java one, the reason that they're named differently is that when you go through JNI, which is the mechanism through by which the Java runtime talks to native code, it has all these naming rules. So you like have to prefix the function with Java, and then there's this escaping sort of sequence where slashes are replaced with underscores are replaced with underscore ones, and it basically creates this mismatch between the symbol names that they're using, that Skiko specifically is using in native, and the ones that they're using for targeting the JVM. And so the way that this manifests into a consumable library is that they pull in the Skia binaries. These are the ones compiled just from the Google project's C++ code. And they're adding their own C++ on top of it, which is the platform-specific adaptations, which knows how to turn the Kotlin native types into Skia types and the JVM types into Skia types. And they're creating their own native library. They're writing Kotlin code, which has those external function declarations. And they're just they're basically trying to get the strings correct so that they match up, so that at runtime, basically when the rest of the compilation happens, there's this phase called the linker, which is going to attempt to validate that those are correct. And this is like very effective, right? Like Compose UI is a wildly effective version of this strategy. If you're using the droidcon app, you're using Compose UI multi-platform, especially if you're on iOS. But like, there's no direct. One of the problems with this approach is there's no direct linkage between that C++ code and the Kotlin code. And so like they get this wrong all the time. If you go look on the bug tracker, like if you try and build Skiko for the ARM targets, which is one of the things we were doing for like this light switch, it'll actually complain because they named a bunch of these things incorrectly. Remember I showed how like the one was surface KT and the other one was surface? Like here they got that wrong in one of them, or like you have to remember the package name and make that correct. Here's another example where like they got the package name wrong. So this approach, while extremely effective, is also like fraught with potential peril if you get these things incorrect. And so the next thing I want to do is take a look at another library called Zipline. And what we're going to do is we're going to kind of evolve the strategy of this Kotlin multi-platform with native library using better and better techniques to like reduce our risk. So Jesse and I gave this talk Zipline a couple of years ago. We've actually been talking about Zipline for 10 years now at droidcons. It's basically a JavaScript engine that we compile and run on our Android and iOS code bases in order to do hot reloading. And the way that we do this without suffering the pain of JavaScript is that it's actually all Kotlin. So we take a Kotlin interface, we take a Kotlin implementation of that interface, and some code that sort of tells the system about that implementation. And we take the implementation and compile that to JavaScript. And so that's all Kotlin running inside the JavaScript engine. But then on the host side, we're still dealing with just that interface. So if you've ever done something like Retrofit or Room, where you have this interface and then there's a bunch of things happening behind the scenes doing HTTP or SQLite, this is basically that, but for JavaScript engines. And so you don't know that there's a JavaScript engine under the hood. You're just writing Kotlin on both sides. And we do this so that we can live reload, sort of hot reload the business logic in the app. All right, this is a zipline project. And to start with, we've taken this is the entry point. The zipline type is like the entry point. And you can see right away we've taken a different approach than what Skiko has done. We actually do have an expect class, so we have multiple implementations for both native and um, the code that's running inside the JavaScript engine. But then the code running on the host side, which is what we call the Android and iOS apps, is talking to this quick.js type, which is the actual JavaScript engine. This is also an expect class, and we do vary it between the version that's for native and the version that's for the JVM. So for quick.js, this is the entry point. So we want to call this, quick.js is a C library. We want to call this C function, and actually this one down here too. And so if I hop over, on the native side, we're actually able to just call these functions directly. And so this is very different than like what Skiko was doing, where they were defining these external functions that the C++ was implementing. We are writing Kotlin, and we are referencing these functions directly. The way that this works is through something called cinterop. Where we're telling the Kotlin build system about the quick.js header, and it's going to automatically generate these type-safe stubs for us that we can then reference, which are then guaranteed to link at linking time. And so we basically eliminated an entire class of error here by having the ability to reference these functions in a type-safe way. So you can see that like they have a return type that is type-safe, and then when I pass that into another function, we get things like nullability, all the structs and stuff that appear in here, and we're able to reference them in a way that allows us to do that safely. So that's a nice advantage, but it's of course in contrast to the JVM version of this, where we actually still have the same problem as Skiko. And so the entry point is here, and I end up calling this create context function, and once again we run into the external function again. So this is another, instead of this function being magically linked on all targets, it's now only magically linked on JVM targets. And what actually happens is we have written C++ code for the JNI. So it has a corresponding function written in C++. Looks very much like the Skiko one, where we're getting the Java specific things. We're doing, casts, and then we end up creating the runtime in here in C++. So this is actually in Android Studio, where like the native experience is not that bad. Like I'm command clicking around and it's working relatively well. And there are actually type hints and all kinds of stuff, but it's still unsafe in the sense that like if I typo this function, it's going to fail at runtime because the JVM is just not going to be able to find it. That like mangling strategy on that page we looked at, like if that's not honored correctly, it's going to fail to link, and then you're going to get a failure at runtime. So like you have to have basically 100% test coverage of this code in order to have any kind of guarantee that this stuff is going to work. One other thing that's different here is that we also have an Android variant. So we're telling cinterop that we want it to do code generation from our headers. We have an Android variant where we have to tell it where the C files are in order for it to compile. There's actually a library we're using called cklib, which we're telling about the C libraries, and it's going to compile it for native. And then we actually have a third build system, which is compiling the native binaries for the JVM. So as part of the effort in Zipline to like make the interaction with native code safer, we actually make the build like dramatically worse because we now have to compile all these different variants of it. So this is an illustration of that. CKlib's a TouchLab project. Actually, I think I have it open. If you go look at it, it's basically going to tell you that you can package C, C++, and Objective-C inside your Kotlin native library inside the klib. But they also have this amazing note that like you can use it, but they're really not going to support it. So if you want to use something like this, you probably should, pay TouchLab. They're a contracting company. They actually built this for us for Zipline when we were paying them. So paid TouchLab their money. So this ends up getting, we have this trade-off now where like we want to introduce this safety because the Kotlin code and the interaction with native is like where we're iterating the most, but we trade it off for build complexity. So we have these, we have the Zipline headers and C files that are fed into these 4 different systems. And then we have our Kotlin code. And in contrast to Skiko, you can see that the header files feed into C interop, which does feed into Kotlin, and that's where we get that safety. And so if we change one of those header files APIs, our Kotlin code for native will fail to compile. But then we have our JNI C++ code that's entirely separate from this system, and that feeds into the Android and the JVM build systems, which produce their native binaries and go into the AARs and jars. And so these ones are still unsafe, where if I do typo them or there's a problem, we're not going to find out until runtime. Real quick, I want to point out that the Zig stuff here, Zig is this, wrong way. Zig is a language, but it also has a build system, and the build system has a C and C++ compiler inside of it. One of the reasons, if you're ever doing this with C or C++, you probably should take a look at this. They have this blog post has an excellent why you should be using it. The compiler itself is dependency free, so there's no like build essentials on Linux. You don't need Xcode on Mac or the Microsoft compiler on Windows. It's got built-in cross compilation. They actually ship all the libcs for like every variant of every operating system, so you can cross compile. And then it has this built-in build system that allows you to this like hyper incremental build system. So it's wildly fast. Like the C and C++ builds we have are like sub 500 milliseconds. Like, you ever remember having a sub 500 millisecond Kotlin build? Never. It's an amazing project, and we're going to look at a little bit of Zig later on. Okay, so next, I want to show this project called Mosaic. Mosaic's a little side project that I have where I've taken, well, so to start with, it's a library for writing command line, like terminal interactive apps using Jetpack Compose. So it doesn't use Jetpack Compose UI. It has its own UI toolkit, but it's still the Jetpack Compose programming model. And it's sort of like build, setup, and structure is evolved from Zipline, so it adds safety on top of that. Real quick, this is not a Mosaic talk, but I can't not. So this is like bog standard Compose, right? Like everybody that's ever done a Compose UI, anything should be able to recognize what's going on here. It's just normal, remembers your states. You got your composables that render stuff, and you got effects. And then down here is sort of like the big different part, which is the entry point is different. And actually this text is like not, Compose UI text. It's like Mosaic UI text. So I want to show this real quick just because it's fun and I can. So this is samples counter. And I've already compiled it, but it's basically updating the terminal. Like I've told it nothing. This is like extremely declarative, right? I've told it nothing that like I want to erase the existing text and write over it. The same way that like you don't tell Compose UI on Android to like erase the previous frame and write over it. It's just like the intrinsic behavior. And so by default, it's rewriting the UI. And so that was actually a Kotlin native. I don't know if you can see like the path here, but this is the Kotlin native version of that. It also runs on the JVM. I'm running on Java 24, which is why it's yelling at me. If I switch to an early one, it won't yell at me. Same output. And then this is like very basic, I would say, on output, but there's all kinds of fun versions. This is my favorite one. It's like a fake test output. It's live updating. So this is all, again, like very declarative compose. Pretty fun. And then the last one I'll do is it does like input and stuff, so I can play Snake. Not rendered very prettily, but works and has keyboard input. This is not a Mosaic talk. It's just, it's fun for me. But the reason that we're talking about Mosaic is that it actually has a native component. In order to do those things, you have to talk native APIs to the operating system, which is just a huge pain. And so the fact that it's multi-platform basically meant that I had to make a choice where I either write it twice or potentially 3 times, depending on whether we want to talk about like JavaScript. Obviously, Node.js can run the terminal, and WebAssembly as well. But I ended up writing the shared code in C because I wanted to write it once and then just reuse it on every platform. And so like this is an example of the entry point. And here's like another function that I have to call, which ends up talking to like the platform APIs. And so I have, where am I here? I don't know why it's not pulling it up, but it's in here. All right, so this is the entry point. And then we're also going to look at this enable raw mode function, which is like the function you have to call after initializing it. It's a little weird. There's actually operating system specific implementations of this function. So like behind the C code or behind Skia in the Compose UI example, like it knows how to talk all kinds of different ways to the actual graphics stack of your computer. So it supports like OpenGL and EGL and OpenGL ES, and it itself is basically exposing a common API in C++ on top of all these things. And so that's sort of another interesting reason to leverage these native libraries is a lot of them themselves are abstracting over platform-specific idiosyncrasies, presenting them in a unified API, but then just in a different language. And so what you can do is then take that and lift it up into Kotlin to leverage that aspect of the library. So like this C library is basically taking these APIs and it's abstracting over Linux and Mac and Windows differences in how they do this terminal setup. I wanted to show really quick, this is like the Zig actual build system. And so you can see like we're building a bunch of different targets of this C code. But the build has a lot of the same things. But one thing I want to show, I don't know why it didn't take me to this. So this is the entry point to that library. It, just like in Zipline, it's also an expect and actual. We vary the class because we have the implementations. In native main, it looks very much like it did in Zipline. We're still using that C interop to get type-safe code generation of our API. But then, unlike Zipline, we actually have type-safe, a version of type safety for the JVM. And so here I'm calling into, this is the JVM version of the function, I'm calling into this JNI class, which is something that I have actually written. It's written in the devil's language of Java. Don't let the semicolons trigger you here. But there's a reason for this. It's that the Java compiler has this, to me, I feel like it's a lesser known behavior, but if you write, so native is like Java's version of external. If you write your JNI code in Java, the Java C compiler will actually automatically produce a C header file with all of that name mangling done for you. It's not really mangling, it's like an encoding scheme. And so in this file, if I were to, rename a function and then run the compilation process, what would happen is this generated header file is actually going to change. And then that will make my C compilation fail, not necessarily my Kotlin compilation. If you want to learn more about this, I actually wrote a blog post about it. And in here, I show off basically that, here's an example where if I change the function from the Java side and then I recompile my code, it's going to end up failing because the header and the C file basically don't line up anymore. And the unfortunate thing about that is this only works from Java, which is annoying. There's a 5-year-old Kotlin issue for supporting the same feature for Kotlin external functions, which would be a huge boon to even projects like Skia and Zipline, where we don't get that type safety because you want to write in Kotlin, right? That's why most of us are here, I would say. And the lack of this function forcing you to Java, lack of this compiler function forcing us to go back to Java is just, it's unfortunate, but it's a thing that you can do. Java actually has another trick that I want to highlight real quick. And so this is this gives us the type safety, but almost from like an inverse perspective, where the source of truth is now the Java code that I've written. And the C compilation is what's going to fail, which is the inverse of C interop. With C interop and Kotlin native, if I change the native function, the header generation is going to fail and my Kotlin will fail. And so you have this weird sort of cyclical thing where if you rename, you can basically have problems on both sides and affect compilation errors in both directions. And ideally, we would have both be going the same direction, which would be the native library is the source of truth. And then our Kotlin code, whether it's JVM based or native based, is derived from that and links against it automatically. Thankfully, as of Java 22, which is about 1.5 years old at this point, there's a new foreign memory access and foreign function calling API. And what this allows you to do is basically from Java define these very, very verbose value objects which represent how to call native functions directly. And while it is very verbose, they were kind enough to provide a tool which is basically C interop, but for Java. And so what it's going to do is take header files and produce Java implementations, not stubs, but implementations which call into this foreign function API. And so that is a thing over here. That is a thing I do in Mosaic. So we have this special JVM JDK 22 source set. It's actually in the build up here. There is a plugin I use called JExtract, which I'm doing. It looks almost exactly the same as the C interop code, where I'm just giving it the header and I'm telling it the package I want it to be generated in, and then I can build a Java 22 specific version of my JVM code, which then calls into these generated functions. And so this is like the code gen, which is just, you can see the IDE loves it. But it's giving you the ability to call into these functions. And then my responsibility really only becomes the same as the JNI C++, which is taking the nativisms and turning them back into Kotlinisms, or vice versa. So here, I take an error, which is traditionally returned as an integer value, and I turn it potentially into an exception. And so now I have achieved the same sort of form of type safety, where the header is the source of truth, and the Kotlin code, regardless of whether it's to the JVM target or to the native target, is derived from that and linking against it. So it basically allows the native code to become almost like a library that I compile against. So this is just the native side of Mosaic. It looks exactly the same as what Zipline should look like, because nothing's really changed here. We're just leveraging C interop. But this is where it's different. This is the JVM side. So we're writing our JNI code now in Java instead of C++. And we leverage the fact that the Java compiler produces this header file, and that allows our Kotlin code now to be relatively type safe against the JNI implementation. And then that header, that JNI header, is fed back into the JNI C code so that the C code is type safe against the Java code, and then it'll get compiled and shoved into the jar. And then in the case of Java 22, we basically do what C interop was doing, but with JExtract, where we feed Java 22 specific Kotlin into a separate Kotlin compilation and then pack that in the jar. And it's only used on 22 and newer automatically. But then remember like Android conferences 10 years ago when you're like, once I get to min SDK 14, like my life will be so easy because I'll be able to drop all this legacy baggage. Like Java 22 is that, but for JNI, because once Java 22 is like the minimum, then my build system gets to look like this with a little extra arrow. I got to feed the JExtract back into Kotlin. But like this is basically the version of what C interop is doing, but for Java, for the JVM. Okay. The very last thing I want to show is that I have written a much simpler sample app, which shows a bunch of different, it's like the world's simplest version of building on top of native code, where I just have a header file that represents addition. And then what I've gone and done is I've added like a C version of addition, a C++ version of addition. There's a Rust version, a Swift version, and a Zig version. And what we can actually do is we can take these and we can build them and run this library. We can pick any language we want and package it into this library. And then there's a command line and a graphical user interface front end to this. So it's basically like the simplest example of taking an existing code base, regardless of language, with the condition that it has to expose, like the whole trick here is that the C ABI, which is like the calling, how you call native code. It's the C ABI is very well defined, and it's basically the mechanism through which all communication across languages currently happens. And so as long as you're using a language that can expose a C compatible ABI, you can use that language. So if your company has some critical library written in Swift, as long as you can expose a C API from it, you can expose a Kotlin API wrapped around it. And that Kotlin API can be itself multi-platform. So weirdly, it can still work on iOS by going through Kotlin multi-platform, or JavaScript, or WebAssembly, or Android, or the JVM on the back end. Or if your team is really into Rust, as long as you can get, these C, you can have it expose a stable C API, or potentially write a stable C API wrapper in that language, maintained by that team building the other thing. It's not that hard to go and wrap a Kotlin multi-platform version of whatever library you're looking to reuse. And so this example is on GitHub. It is not public, which I will do after this talk. But I want to reiterate that the point of going through this and showing these libraries is that this is already being done. Compose UI is certainly the best example of this. You sort of feel that Compose UI is Kotlin putting its best foot forward, especially Compose UI multi-platform. And then the ironic thing about that is it's actually C and C++ putting their best foot forward in the fact that we took this really amazing 2D rendering library and made it run on all these platforms just with this really nice thing put in front of it. And so whether it's a third-party library like FFmpeg that you want to wrap, or your company's own internal libraries, maybe you just have a team that's extremely well versed in Rust, or you have a code base written in something like Zig or C++ or whatever, you shouldn't have to feel like that's an impediment to leveraging that on Android or iOS, or basically through any of the platforms that Kotlin targets. You still can use those things. That's all I got. Thank you very much.